Please get to this page number, not telling me because it's 15, page 15. Right, now listen up please. We have 5 lessons between now and your first test, which is the interim test. And Airtame is not seeming to be cooperating with me. We need to get this done today. There's a few pages I need to get through. Then we have 4 lessons next week. The practical that's scheduled for week 4, we don't have time to spend a lesson on, so we're going to have to do that after the test. All right. So even though it says week 4 in the guide, it's going to be done after our week 5 test. So we looked at specific heat which required a change in, or which produced a change in temperature. You throw some energy at a substance, they start to jiggle faster, their temperature increases. They're gaining kinetic energy. That's the key thing. When heat is supplied, the internal energy of your substance, which is the sum of potential and kinetic energies, increases. Well, if we're not at a phase change, if we're not at a boiling or a melting point, it's only the kinetic energy that increases. And we measure the increase in kinetic energy through an increase in temperature. Eventually, we get to a point where they're jiggling so much that any extra energy doesn't go to any faster jiggle, it actually puts them further apart. It goes into gaining potential energy. When you're providing heat to a substance, when it reaches this special point where all of the particles are now suddenly changing state, they're not jiggling any faster. Their temperature remains latent. That means not changing. And so that's why it's called the latent heat. Because even though you're throwing energy at the substance, we're not getting a change in temperature. We're getting a change in potential energy. Okay? And so I need to flip my screen and we're going to start writing. And it might be that I might just keep teaching into period 6, which I have a dot, and then you have to go home and watch it on YouTube because I know you've got a test coming up. But anyway, here's the thing. The proportionalities are that Q is proportional to mass. So write that down. Then that's... Oh, no. Oh, no. Hey, hey, hey. See, you're at the best school in the state. No offense, ladies. And we can't even organise.
Can't screen capture a whiteboard, you go.
Hang on, I'm just going to turn Airtame off. It's saying it's already in use. Oh no, go figure. Alright, did it stop? No. Share screen. Already in use. Yeah, that's me. I'm going to... And I've just expressed to you how we don't have any time to be mucking about.
Next period starts at 2
Sam,
I'm not going to be at 7. You're missing. I'll tell you what, I was waiting.
Sam, could you please tell me the IP address? .20. Yep. Yep.
what am I going to expect?
You want to get access? Yes. Because like the wind's down, but it's going to be a cold day. There is no wind. You want to be a warm day with no wind. A cold day with rain. Or even a cold day with rain.
This is absolutely disgusting.
Is this the one where like you start into the water and you see like the rain coming towards you, it's just looks like smoke, and you like realize and look up and you just go straight away. Like I think it was in the first place
I swear to God. Last year I had so many urges of just taking the MacBook and just flinging it as hard as I could like a frisbee at the brick wall. Like, one day I'm going to turn up to IT with my Surface and go, oh, it must have fallen off the table. Because this is just absolutely pathetic. I'm still screen capturing. I might just send that to IT. This is
So do it old fashioned. You got the mark right one. It is. Over box. No. Factorial is like non-factorial.
Alright, now I'm in tablet mode, so I can't even use my keyboard.
Why does factorial is
Absolutely. Alright, what was it? 10.20.41. Was it 41.1? 0. 486.
Easy job, like 13 marks. Last section.
Only 13? Was the last two questions?
Alright, here's where we're at. The heat required is proportional to the mass. This should make sense. The more particles you have, and you want to gain or provide extra potential energy, you've got to put in more heat or more energy. It is not proportional to a change in temperature, because what happens is, and I'm about to write this big fat red cross, there is no change in temperature. When you're going through a phase change, the temperature remains constant. It's proportional to this value called L, and that is the latent heat. It's specific or unique to each substance. It's basically down to chemistry, how close the molecules are being attracted to their neighbouring molecules, interatomic forces. The stronger the forces, the closer they might be, the more energy you have to rip them apart. Now, it's L, but we've got two. We've got Q equals MLF, and this is called the latent heat of fusion. Fusion is going from solid to liquid, or liquid to solid. So you can go both ways if you add heat or remove heat. Then you've also got Q equals MLV. The V stands for vaporization. And that's liquid to a gas. Okay? And so L, if we rearrange, that's going to be Q over M. That is going to have the units of joules per kilogram. So when you look at the latent heats that are given in tables, you basically, that number, imagine that's how much energy you need to give to a kilogram of a substance to either melt it or a kilogram of a substance to boil it. You need to also remove that energy from the substance to go the other way. Okay? Now here is a common heating curve. I've given you the common heating curve. Could we please put delta T in degrees Celsius on the top, and could we put the heat energy in joules at the bottom? Now, you can see we've split this. Let's put the states solid, liquid, and gas. Okay? And so obviously, if we heat up a solid, we'll call this Q1. Okay? And we have an equation for that. That's MC delta T. And you can see as we go along the Q value, we're increasing temperature. So if temperature is increasing, then all of that Q goes into increasing the kinetic energy. Okay? Then eventually we get to what's called the temperature of which it melts. And this is again going to be unique for each substance. So if it was water, I would be writing 0 and 100. But this could be for any substance that goes through these three phases. So we'll just leave it as melting point. Then, this section here, this is the latent heat of fusion. So now, once we reach the melting point, oh man, what?
Oh. 28,000.
Is that what it is now?
Yeah, I think so.
It's all the apocalypse.
Money well spent.
The Wi-Fi's dropped out. No internet, but secured. Thanks. Don't worry, I'm going to be sending a lovely YouTube video to IT help desk. What now? 1762. Thank you. I appreciate your... All right, that's what I was talking about. You're like, what the hell is Mr. Murray talking about? That's what I was talking about. Okay, so imagine we're adding Q. We're going along the x-axis, and we're increasing temperature until we reach a point which they're all jiggling at such a rate that any more energy does not increase their kinetic energy. It increases their potential. And we need to do that for every single particle until they've all been melted into a liquid. That is called the latent heat of fusion. Okay? Now I'm going to draw a dashed line down to here, and I'm going to call this part Q2. Yes, what is it? What is that? Melting point. So as I said, if it was water, that would be 0, and then up here would be 100, but any substance will have its own temperature at which it would melt. Now, we have an equation that is equal to MLF. At this point, we are not increasing the kinetic energy, we are increasing the potential energy. Then, once they're all dancing and jiggling in their increased state and position, now we go into the liquid state where we've got Q3. Now we're back to an MC delta T. Again, we can figure out how much is needed, and that is going to cause an increase in kinetic energy. Okay? We then reach the next state, which is the phase change. That is the latent heat of vaporization. And again, this will be different to the fusion. So for water, the fusion value and the vaporization values are different. We've got to look at them up on a table. MLV, same deal, an increase in potential energy. And then lastly, in our gaseous state, it will cause them to jiggle more. It'll cause a temperature rise, and we call that MC delta T, which is an increase in kinetic energy. Okay? So this is the problem. If we are going through various phase changes, if we're taking ice at -5 degrees to water at 20 degrees, you've got 3 different sections, Q1 plus Q2 plus Q3. You have to split it up into 3 different heats, each having their own equation, each having their own specific values. Okay? This should really have been on the bottom of that page. It's called so as there is no change in temperature. The heat added contributes to the potential energy of the system, not the kinetic. The analogy would be a bowling ball rolling along, okay, with a certain velocity, which would be a certain kinetic energy. At some velocity, it has this is where it breaks down, but if we could rise that ball up a certain height, now, due to its state or position above the ground, it has more potential energy. You keep rolling it, getting faster and faster, and then eventually it might get up to this third step, where it's now even higher above the ground. And so now I could ask you a question. Would you rather a bowling ball roll along the floor at 4 meters per second and crack you in the ankle, or have it rolling along the table at the same speed and then fall down and crack you in the ankle? Students that have an understanding of energy would go, well, hang on, the ball on the table has more energy. It's got EK and EP. And so as it falls back down, it's now going to convert that EP into more EK, and it's going to smack my ankle with even more energy, kinetic. So I would take the ball on the ground. Remember that when we discuss steam at 100 degrees or water, liquid at 100 degrees. They both have the same temperature, but one is far more dangerous because the steam has more potential energy. And since it's generally at a higher temperature than your flesh, it's going to throw all of that extra potential energy to your flesh and cause more severe burns. That is a common question that likes to be asked about which would you rather. All right, here are our tables. We generally just play with water. In tests and exams, water is the easy one to go to because the latent heats of water are in your data sheet. So it's just an easy go-to. But we could look at metals, we could look at ethyl alcohol, we could look at oxygen. Okay? But if we need to know at which temperature does this energy, at which temperature is this energy required? Okay? So, let's have a look. Melting ice at 0 degrees. Well, okay, we're already at its melting point. This is a very simple Q equals MLF. Okay? Now, I've thrown in a curveball here. I've given you a mass which is not the SI unit. So we do a little side mission. 0.02 kgs. We then go, well, I can take this equation over here. Please, come on, please. No, I'm asking nicely. What just happened? Everything's just been shifted. Sorry, give me a second, please. This is all right, we seem to be back. Well, I can't do that, so I'm just going to write it again. Now, be careful. We haven't looked at vaporization. In fact, this table is just for fusion, so that's melting. We need to use this value. 3.34 times 10 to the 5 multiplied by its mass gives 6,680 joules. That's how much energy is required to give... 20 grams is like a nice big ice cube. At its melting point, it requires 6,000 joules. Even though the temperature doesn't change, all we have done is taken ice at 0 degrees and it's now water at 0 degrees. On the curve, all we have done is gone through that. Okay? We didn't raise it up from -10 to 0. We didn't take the water from 0 to 10. We've just gone across the latent heat. And so we just needed one equation. But it doesn't stay that easy. Let's look now. So, now, it pays sometimes to very quickly sketch a heating curve and figure out where we are at. So we're currently here, negative 20. Not only do we need to get our, that's Q1, we need to get our ice, from minus 20 to 0. Then we need to get it across to here. Okay, so we need two different equations. Q1 is going to be the latent heat of fusion, and then Q1 is increasing the temperature of our ice to its melting point. Q2 is then the latent heat of fusion. So I would like you to sketch the heating curve, and then just write that the sum of the heat is Q1 plus Q2. Now, here's where we're going to start using subscripts, because now we've got ice, we've got water, we've got gas, or steam, if we went that far. So I'm going to say M ice, C ice, delta T ice, plus M ice, latent heat of fusion. All right? Now you start plugging everything in. Well, again, side mission, 40. So 0.04. Now, here is a big area where students stuff up. What? A common error is that they use the wrong specific heat. Ice has a specific heat of 2,100, and lots of students just write 4,180. That is only for liquid water. And I can say this 5 times between now and the test, there are students that will still put down the wrong specific heats. It's a common error to make. So make sure it's 2100. Final minus initial, well, that just gives plus 20, but I need to show all my working out, plus my 0.04, 3.34 by 10 to the 5. Okay?
Why didn't you do the side mission for the delta T?
Well, because if I wrote that, that number was calculated. And so I did it mental maths, but you've got to write that down on the page. Seems a bit silly, but you don't want to risk losing marks. Okay? I'm just going to evaluate these intermediate steps. The first is 1,680, and then the second is 13,360. And so we get 15,040, or 15.0 by 10 to the 3 joules. Okay? It's a lot of working out for a question that is only really worth 3 marks. Writing out your equation would be worth 1 mark. Working out the values here would be 2 marks. And then expressing your answer in correct significant figures and units would give you that 3rd mark. Yes?
So we're not to be like 1,680 plus there.
No, you could omit that step, but I just wanted to show you, look at how much energy, there's more energy required to melt the ice than get it from minus 20 to 0. Okay? Next! What?
Oh, it's just nothing.
Let's just sketch a heat. Let's just get a heating curve, please. We are going from minus 4 to 0. We are then melting, and then we are going from 0 to 24. Okay? So again, we require 3 different steps. Q1, heating the ice to its melting point. Q2, melting the ice completely into a liquid. And then Q3 is heating the liquid water to 24 degrees. Okay? So, sum of all energies equals Q1 plus Q2 plus Q3. I'm going to write my subscripts again because these are now becoming more important. Mass ice, C ice, delta T ice. Mass ice, latent heat fusion, plus mass water, C water, delta T water. Okay? 1.4 by 2100, 0 minus plus 1.4, 3.34 by 10 to the 5 plus 1.4, 4180, 24 minus 0. So, that is because of that. That is because of that. Okay, again, students will stuff this up. It's the same mass. In different states, they have different thermal properties. Okay? We still have 5 minutes, which is good because we've got one important thing to figure out. I am going to evaluate this step numerically again. 11,760 plus 467,600 plus 140,448. You don't need to write that step out. Calculator gives 619,808, 6.20. In fact, 6.2 by 10 to the 5. Could somebody explain to me why I chose 2 sig fig? Everything's 2 sig fig. All right, so we just go 2 sig fig. All right. Gentlemen, please, I'm not really in the nicest state of mind due to the IT issues. Can you just stop with the talking and the chit-chat? This is really important stuff, and I seem to be the only one that cares that we're running out of time. I want to put a very important note here. No, I don't. I want to sketch the heating curve first. So could we please sketch the heating curve? Lead at 347. I'll give you a quick pro tip. Lead melts at 327. So we are currently up here in its liquid state. We need to cool that down, then solidify it. Okay? So that's going to be Q1 and Q2. Now here's the thing. With Q1, it will give you a negative value because your delta T, it will be negative, right? You do the T final minus T initial, and if your final's less than your initial, you will get a negative value. And we spoke about heat flows both ways. A negative Q means losing heat. A positive Q means gaining heat. However, there is no plus or minuses in this equation. We have to manually enter the negative. Did I spell losing? You have to enter it manually. Okay? Again, this is another area where students make common mistakes. They add a big number to a negative number. And if the conditions are right, you get 0. Well, how did that happen? 0, So just before we run away, Q1 plus Q2, we'll go MC delta T plus minus MLF. We had half a kilo of lead, which we're going to say that it has a specific heat of 130. 3, we were at 347. Final, 327 minus initial, 347. That gives a delta T of negative 20. We are then going to subtract a further, okay? This, again, that was from our table. We were told the latent heat of lead was that, and so the numbers give minus 13,800 joules, which is 13.8 kilojoules removed. Okay? All right? I sure can. So, lots of things to be aware of. One final note that I wrote for the other year is that a positive MLF is melting or solidifying, and a negative MLF would then be the opposite, which would be freezing or solidifying. Okay? So, two important cautious things here. There will be some really tricky calculations in the test. The first common mistake is mixing up your specific heat capacities of ice and water. The next one is forgetting to manually enter that negative if you are going backwards in your heating curve. If you're going backwards, all of the Q's must be negative. The delta T's will give the negative. You have to manually enter the latent heats. Zach, you missed a crazy lesson. The first half hour was me just swearing at the laptop because the Wi-Fi kept dropping out. So just go home and watch it. Huh? Yeah, no, I'm probably going to keep teaching until Yep. All right, see you guys. And do I just I'll keep teaching. I'm going to keep talking and make you watch the rest of the video. Yeah? Well, everyone just started leaving. I understand you have a maths test. So go to your maths test. Go to your maths test. Well, I'm going to keep talking about boiling. I'm just going to sit here for half an hour and just keep teaching, and then you can watch it at home. And I'll email everyone and say, I want you to watch this. Is that alright? Can you watch it over the weekend?
Yeah, I should be.
And then if you're still unsure, come to the help session on Monday and we can go through it.
Yeah.
Yeah?
No worries.
Cool. No worries. I hope there's no class here. Guys, I'm just going to keep teaching. I'm going to screen capture this and I'm going to send you all an email to say just keep watching from 40 minutes to 60 minutes. Alright, I hope you don't mind. Yes?
Just on manually entering the negative.
Yeah.
Are you entering it just here, or is this the?
Well, so that would be negative 20.
Yeah.
So I omitted the intermediate step, and I didn't do it last year. So that would be negative something, and that would be negative something. And so in your calculator, if you do that whole line, you're just adding two negative values. You're getting the negative Q to cool it down to its melting point,
Yeah.
and then the negative Q to then remove the extra potential energy to solidify it.
So if I entered that into my calculator, I would get this
Yes.
as a negative. So
As
I
a
don't
negative.
have to change.
No. I mean, if you wanted to, you could put negative 20 there.
Yeah.
So you're still going to get a negative value, subtract a value.
Negative.
You're going to get two
Yeah.
negative values.
And with this in a test, we write it as a negative or
No.
as
So
that removed?
I'll be more explicit, but yeah, try not to have plus or minuses. Just say removed
Okay.
afterwards.
Yeah.
Cool. All right. No worries. Stop airtime. I'm just going to keep teaching. And hopefully there's no class in here. All right, see you ladies. Apologies for the IT issues. Good, I think. All right. So, now that we're alone, people, I'm going to keep going. 20 minutes. I'd like you to watch from this point to the rest of this, to the end of this video, and we're now going to look at latent heat. Now, there's a nice little explanation as to why there's more energy required to boil a litre of water than it is to melt a litre of ice. If you compare this number, this is 22.5 by 10 to the 5 joules per kilo, and if you go back to the fusion, it's only 3.34. So it's nearly 10 times greater, the amount of energy to boil water than it is to melt it. And it has to do with the spacing. So if we looked at going from a solid to a liquid, we have to do work on it. We have to apply a force over a distance. And it turns out that the increase in distance isn't that great. So we go from a really close together to a little bit further apart. Well, it turns out that when we go from a liquid to a gas, we have to pull these molecules apart by a much greater distance. And so when we use our work equals F times S, a much greater distance, that gives a much larger latent heat. Okay, this question came up a few years ago in a test, and it may not have been taught, but a lot of students sort of struggled. So our terminology here, energy required to boil. Again, while you're doing these first few questions, it's always helpful to sketch where are we. It's at 100 degrees, so it's already at its melting point. We're simply doing that. Okay, so this is again just a latent heat of vaporization. So Q equals mLV. We take our mass, we take our value 22.5 by 10 to the 5, and we get the energy required. Okay, and wouldn't you know it, I don't actually have the working out in front of me. Oh boy, you're going to have to figure out what this answer is and write joules gained. You don't have to write gained or removed because it's already sort of expected in the question or implied. But I am going to leave you with this one last question. Let's sketch the heating curve, temperature over energy. That's a Q, sorry. All right, here we go. Zigzag, zigzag, zig. Steam condense. Okay, at 133, so we're way up here. We're going to cool it down to its boiling point. We're going to condense it this way. And then we're going to go down to 38 degrees. So again, Q1, Q2, Q3. I've put this question in again because we're going to have negative Qs, negative Qs, negative Qs. Okay? So where were we? We were at 133. So the sum of the heats is Q1 plus Q2 plus Q3. We will write M steam, C steam, delta T steam plus M steam LV. Now, we now need to remove that. So how about we just put him in brackets, minus that, plus M water, C water, delta T water. Okay, so remember, and I'll put a little note here, that's 4180. This one here is different. I believe it to be 1,000. And I'm not quite sure of that, so I'm just going to quickly zoom out and check my specific heat capacity booklet. Check that my table gives a specific heat of 1,000. Bear with me, gentlemen and ladies. Steam, 2,000. Oops, I was close. 2,000. So I'm going to go in and quickly edit that. Okay. And hopefully I don't think I'll be able to do it, knowing my luck. We've got mass equals 0.125. 2,000. Now, final minus initial. Well, the final was 100 minus 133. Again, don't just write minus 33 because you have to show you working out. Minus 0.125, 22.5 by 10 to the 5, plus water. Oh, now I forgot to add the mass. Run out of room. M is 0.125. Specific heat capacity of water. And then our delta T final is 38 minus initial was 100. So again, that's your negative 62. This one here is your negative 33. And so that's your total energy. So again, remember, where did I put my negative? There's my, I wanted highlighter. There's my negative because we're condensing. Okay, so condensing means gas to liquid, meaning Q is being lost. Q lost. Okay, so remember that. We will get three negative terms. That, negative that, take that, negative that, and you will get your answer down here, which you will work out for me, and you will place it there. Now, this was the lesson that was intended for today, except for the technical difficulties. Again, I would encourage you to get this done, possibly not for homework, but complete ASAP before test week 5. Okay, please get that done. So there are some practice questions there for you. So please get these questions done and I appreciate your extra 20 minutes of watching this last bit. There were a few important things in this lesson, and it might pay for you to summarize them in your own summary notes. So I will stop now. See you later.